Hi, this is Joey Gugliardi, and this is my Monte Carlo 5 lab, optimization part 2. So for this lab, it was made up of 3 parts. The first problem being the TSP that we made, the genetic algorithm for the TSP for 10 stops. We wanted to see if we could improve that. And so what I did was, from Professor Rich's work on the multi-load TSP in MATLAB, I took the mutations and the tournament method. So I added to the original TSP a genetic algorithm. I used a tournament method that performs 4 mutations on the best route taken from the population and from a random sample from that population. And then once it mutates on that best route, it makes that the new population. So as you continue down your iterations, you're going to be getting better and better. So I wasn't going to go through the entire pseudocode last time because the lab before this, I went through the pseudocode for my TSP problem, but this is the pseudocode for the improvement that I added. So basically what I just said, it creates a matrix of random order that it contains a random permutation of numbers, just basically randomizes where you'll be pulling from the population. For every 4 iterations from size 4 to the size of the population, you're taking 4 of those routes. So this would be taking the 4 of the routes, and then this will be taking the 4 costs of those routes. And then based on that, we take an array that takes the best of those 4 and saves the route in there. Now, this is where we get our insertion points. So we'll take 2 insertion points, a random number from 1 to the number of stops, which in this case is 10. And the first insertion point will always be greater than or equal to the second insertion point. Or sorry, less than or equal to the second insertion point. So now when we get into our mutations, for each iteration, k to 4, so for each of those 4 that we chose, the best layout will be set equal to each row. So basically we're taking that best from the population and we are keeping it the same for the first one. The second one, but our first mutation, we will be flipping on elements I1 and I2. The third mutation will be swapping elements I1 and I2. And the last mutation, we will be sliding element I1 down after I2. Then after this, we create a new population based on the temporary population and set the original population equal to the new population. And through all this, of course, calculating which costs are best based on our swaps. So the entire MATLAB code for the problem is here. I highlighted what I added. So then, in conclusion, we were able to improve the original TSP problem by adding more mutations and a tournament approach to ensure the algorithm gets better. So now, problem 2 was improving the 25 stop TSP, and I added 2 improvements. The first improvement was this. I noticed that the insertion points could be equal to each other, and the issue with that is the insertion points, if they're both equal to one another, there is no mutations going on. So I wanted to eliminate that. So I initialized and set them both equal to 0. And while insertion point 1 is equal to insertion point 2, I wanted this to loop. And so basically, while they're equal, I want it to loop until they're not equal. And then that would ensure that mutations would happen. So the result, the improvement will eliminate the iterations that the algorithm does not mutate when the 2 insertion points are equal. Second improvement that I added was basically a new mutation, which was called a scramble mutation. So basically what this was going to do was, once again, we'd get our insertion points, and basically what it's going to do is take the length of that insertion point equal to the value of the insertion point 2 minus insertion point 1 plus 1. And then, so for every value from 1 to the length, there's a loop, and you want to set the array of values, val. You want an array of those values, basically all of the values that are between I1, insertion point 1, and insertion point 2. So then you set the set it equal to the temporary population matrix. So then you set the temporary population matrix, the current row equal to elements I through j, equal to the randomized elements of array val. So basically it's taking all those elements between insertion point 1 and insertion point 2 and randomizing them and placing them back in the array here. And then you want to clear all the elements of that val. So I got it to work. It took a lot of work to make that happen, but sure enough, the mutation works. The result, this improvement adds a new mutation that will scramble the stops between I1 and I2, like I talked about. It's not been proven better than flip. So I concluded that after running, I did 2 with my scramble and my improvement 1, which was eliminating the routes, or sorry, when insertion point 1 and 2 are equal. And as you can see, this was the route distance for each of these. And in fact, the flip shows to be even a little bit better than the scramble. But if I swapped out the scramble maybe for the slide or anything like that, it might get better. Actually, this was for the slide. I did not try it for the flip, which replacing with the flip might be better because a flip is a big change, just as the scramble would be a big change, where a slide and a swap are smaller changes. So here's my code for this. What I added, my mutation, my improvement, and my mutation are highlighted there. So then, okay. Lastly, my problem 3, I wanted to use DEA combined with simulated annealing. So I initialized some variables here, and I'm sorry, this should not be here. So the result was to find the appropriate efficiency values for all of Liberty University's departments, DMUs, given both their inputs and outputs. So we want to initialize all the variables, and then basically this is a giant iteration from 2 to the number of iterations, which would be 10,000. And basically what's going to happen here is you create a matrix output mult that multiplies the outputs by the output weight, and then out department gives the total outputs for each department, and then you have the total output, which is all of the outputs in that matrix combined. And then you have input mult, so it does it for outputs, which is here. It does it for inputs, and basically what we have here is we set a counter equal to 0. If total output minus total input is less than or equal to 0, then we enter this inside here. So then for each department we have a loop. So that's one of our constraints, is that outputs over inputs should be equal to 1. Sorry, should be less than or equal to 1. So we linearize that there. And then down here we have another constraint, which is basically to linearize our DMUs. We want to set the denominator equal to 1, but obviously we can't hit exactly 1, so we have 0.98 to 1.1. So in depth, which was above each department's total inputs, should be greater than 0.98 and less than or equal to 1.1. So they should be 1 essentially. And then just to see how many of our departments do that, we increment the counter by 1. And if one of them does not, we want to break that for loop and be done, because we need all departments to be equal to that within those bounds. So then if counter is equal to the number of departments, which means all the departments, inputs, or 1, for each department we have a loop. And basically this is where the simulated annealing is happening with the theta candidate and the theta current. And basically this equation here is our maximization equation. So we're trying to maximize our thetas for each of them, maximize our efficiencies. So if it's greater than or equal to a random number, this equation, then we enter into here. The theta current is now set equal to the theta candidate. And if this is not the case, then theta candidate is set equal to theta current. So we would go back. If it is, then we take it. We take the candidate. We set current equal to the candidate. If it's not, we go back to the current. Now, if theta candidate is greater than the best for the current department, then we set best of that current department equal to theta candidate. End if, end for loop, end if. And then at the very end of this giant loop, we have set temperature equal to temperature times 0.95. That's our cooling factor. We're simulating annealing. We'll keep running until it needs to stop. Basically, I've written out my code, my MATLAB code here. I am getting all zeros. I'm having some issues with the code, but I've worked long on it, and I need to work some of those issues out more. But in conclusion, simulated annealing with random search can be used to solve for the weights of the input and outputs in data envelopment analysis in order to solve for the efficiencies for the DMUs. And like I said, I couldn't get my code to work, but I will continue to work on it. I think I have a good base here. So yeah, have it all in MATLAB as well. So now going into MATLAB here real fast, I'll just show you just real quick the scramble mutation. Elements 3 to 6, if I is 3 and j is 6, should do these guys right here. 7, 6, 5, 4, 3, 4, 5, 6. So it should scramble those down here. Let's run it. 7, it went 6, 4, 5, 7. Let's try it again. 6, 5, 7, 4. 7, 4, 6, 5, while keeping the other elements the same. So this shows the scramble mutation. Thank you for watching.